This will be a walkthrough of the AQA GCSE Chemistry 2023 Higher Tier Paper 1. Question 1. Discoveries in chemistry led to a better understanding of atomic structure. 1.1. Atoms were originally thought to be tiny spheres that could not be divided. The plum pudding model of the atom was then developed. Figure 1 represents the plum pudding model of the atom. Describe the plum pudding model of the atom. Well, we have to remind ourselves about when this was discovered and who this was discovered by first. Well, the plum pudding model was discovered by Thomson. Now, at this time, there was not an understanding of protons, but in our model, we can see something that is positively charged, which is our large circle. And within this positive charge, we have smaller negative charged circles. So, what our understanding of the model is then, is we have a large ball of positive charge with small negatively charged electrons that were embedded in it. And that's what we can write for our answer. (1.2) Atoms contain electrons, neutrons, and protons. Write these three particles in order of their discovery. Well, as we put in our answer for our previous question, we have identified electrons at this point, so that will be our first subatomic particle discovered. But then, after that, it would be through the work of Rutherford, we'd be able to identify the positive charge particle, which is called the proton. And then lastly, discovered by Chadwick, would be the understanding that there are neutrons. Very few atoms of the element tennessine have ever been identified. The atomic number of tennessine is 117. Predict the number of outer shell electrons in an atom of tennessine. Give one reason for your answer. Use the periodic table. So if we look and find the periodic table now, look for tennessine, we realize that tennessine is in group 7. Now, what's our understanding about elements that are in group 7? They all should have 7 electrons in their outer shell. So that will be our number of electrons in the outer shell, 7. And then the reason is because tennessine is in group 7. (1.4) Tennessine was first identified by a small group of scientists in 2010. Suggest one reason why tennessine was not accepted as a new element by other scientists until 2015. So 2010 discovered, not accepted by other scientists until 2015. Well, one might think that it may be due to new evidence and further evidence being found and then allowing more scientists to accept the work. Well, we have to remember what it says by other scientists. Now, usually when some scientists discover something, they want to make sure that that work that they have discovered is true and not any false claims are made. So they give their work to other scientists to check it, and that is known as peer review. So what actually probably had happened between 2010 and then 2015 was peer review was carried out. It's not asking us to explain the reason why. It's just suggesting, and that is a logical suggestion. 1.5. The discovery of isotopes explained why some relative atomic masses are not whole numbers. Element R has 2 isotopes. Table 1 shows the mass numbers and percentage abundances of the isotopes of element R. So in element R, we have two isotopes, one with a mass number of 6 with a percentage abundance of 7.6, and one with a mass number of 7 and its percentage abundance is 92.4. Calculate the relative atomic mass of element R. Give your answer to 1 decimal place. So for us to find the RAM, which is the relative atomic mass, we need to use a specific formula. And that formula is going to be mass number 1 multiplied by percentage abundance 1. And then add that to mass number 2 multiplied by percentage abundance 2. And then, once we get our total there, we need to divide that by 100. So, let's calculate our first part of our equation. So, taking the mass number, which is 6, and then multiplying that by 7.6, we then get a value of 45.6. So, it would be 45.6. We're going to add that now to 7 multiplied by 92.4. And we'll get a value of 646.8. And then we're going to find a total of that and then divide that by 100. And we should get our final answer. So 646.8 plus 45.6, that gives us a value of 692.4. And then we divide that by 100. And then that should give us a value of 6.924. Remember though, they asked us to give our answer to 1 decimal place. So putting that answer to the 1 decimal place would be a value of 6.9. Question 2. This question is about temperature changes. A student investigated the change in temperature of a solution when different masses of ammonium nitrate were dissolved in water. This is the method used. 2.1. Give the independent variable and the dependent variable in the investigation. A reminder for our variables, independent is what we change, and dependent is what we measure. So reading our method carefully now, says we're going to measure 200 centimeter cubed of water into a polystyrene cup. Even though it says measure, they're giving us a specific value. So this is probably something that we're going to keep the same if we're going to repeat the experiment. So this would actually be a control variable, but it's not asking us for that. Measure the temperature of the water. So there is something that we could measure. So the measurement has to be with temperature then. So let's read on and see if there is anything else to do with temperature again. Add 4 grams of ammonium nitrate to the water. Again, a specific value. Is also another control variable, the mass of ammonium nitrate. Stir the solution until all the ammonium nitrate has dissolved. Measure the lowest temperature reached by the solution. So again, measure, but this time lowest temperature. So we've got 2 points in which we're measuring temperature. 6. Repeat steps 1 to 5 with different masses of ammonium nitrate. So we are actually using different masses of ammonium nitrate. So even though it says 4 grams of ammonium nitrate, we initially thought that was a control variable. By reading step 6 now, we know that that's not the control variable. That's going to be the independent variable. So our independent variable is mass of ammonium nitrate. But what about our dependent variable? Well, as we said, step 2 and step 5, they're asking us to measure temperatures. But if we measure the temperature at the start and then we measure a temperature at the end, well, it probably is going to be then a change in the temperature. So that could be an acceptable dependent variable. But ultimately what we want to do is we want to measure the lowest temperature. So instead of saying change in temperature, we could actually say the lowest temperature of the solution. Table 2 shows the results. So first column, mass of ammonium nitrate. Second column, lowest temperature of solution. So again, even if we weren't sure about this previous question, we could look at the table, because every time we have a results table, the first column should be the independent variable and the second column should be the dependent variable. So it does match what we've put for these answers to our previous question. 2.2. Plot the data from table 2 on figure 2. Draw a line of best fit. Once again, look at our scales and our axes. Mass of ammonium nitrate added in grams is on the x-axis. X-axis should be the independent variable on a graph. Lowest temperature of solution in degrees Celsius, that's y-axis, and that should always be the dependent variable. So we need to plot the data from table 2 first. So a mass of ammonium nitrate 4 grams, our lowest temperature of solution is 18.2. So we find 4 grams, and we need to find 18.2 on our y-axis. Well, let's check what our x-axis is going up in right now. Looks like it's going up in 0.5. So if our middle here is 2.5, we need to go up until we get to 4. So 4 should be here. Let's find 18.2. So look at our scale on our y-axis now, what are the intervals? So this is 18 and 20, so halfway between it is going to be 19. So this is going up in 0.2. So we just need to find the link there, and that's where it will be. Next one, 8.0 is our mass of ammonium nitrate, and 16.2 is our lowest temperature. So finding 8 now. Middle between 5 and 10 is 0.7.5. So 8 will be here. So finding 16.2 now. So going up, 16.2 should be here. So we've done our first two. 12.0 to 15.2. So we need to find 12 now. So midway will be 12.5. So there's our 12. And then we want 15.2 now. So that's halfway between 14 and 16 is 15. So one above would be 15.2. Should be here. 16.0 for our mass. 13.6 for our lowest temperature. So 16, halfway between 15 and 17.5. So it's 15.5, 16 is here now. And then we want 13.6. So we know halfway between 12 and 14 is 13. Now it's going up in 0.2, 0.2, 0.4, 0.6. So there's our 13.6. So we've done the next two more. 20 and 12.4. So we've got 20 there already, so 12.4 is what we need. So then that would be at this point. And then our last one, which is 24 and 10.6. So we've got 22.5 is midway. So we want 24 So 74 is going to be here, and then we want 10.6. That's 10.2, 10.4, 10.6. Okay, so we've plotted all our points now. The next thing that they're asking us for is to draw a line of best fit. So remember that a line of best fit needs to go through as many of the points as possible. Best idea at this point would be to do straight line going through as many of the points as possible. And there is a suitable line of best fit going through as many of the points as possible. 2.3. Determine the initial temperature of the water. You should extend your best fit line on figure 2. So we need to think about extending the line of best fit. Now, when it means extending the line of best fit, we want to get to a point where the line is touching the y-axis. Because when it's touching the y-axis, that should be when there is no ammonium nitrate. So that should mean it's at the start of the experiment. So if we try to extend our line of best fit to the y-axis now, we've done it here, and finding the reading on the y-axis now, remind ourselves that it's halfway between 18 and 20 is 19, then reading up is touching the y-axis around 19.6, 19.7. So we can write that as our final answer. 2.4. How do the results show that dissolving ammonium nitrate in water is endothermic? So the keyword endothermic here, that's taking energy in from the surroundings. So if it's taking energy in from the surroundings, that will mean that the temperature is decreased. So a decrease in temperature makes us identify that the equation, the reaction, is endothermic. The student repeated the experiment 3 more times. Table 3 shows the results for 8 grams of ammonium nitrate. So our 4 trials, and then a mean has been calculated for those results. 2.5. The student recorded the mean lowest temperature of the solution for 8 grams of ammonium nitrate at 16.5 plus or minus 0.3 degrees Celsius. Explain why the student included plus or minus 0.3 degrees Celsius after the mean lowest temperature. So it's what does this value represent? Well, we know that the 16.5 represents the mean, but this plus or minus 0.3 represents the uncertainty. So 0.3 plus or minus is the uncertainty. Now, where does this uncertainty come from? Well, the uncertainty can come from the apparatus that's used. Because remember, in the apparatus that's used, they all have their own measurements. So the thermometer, for example, is what's going to be used to measure the temperature. So the thermometer, because it's got intervals, measurements, it could be read wrong by giving a higher temperature than normal or a lower temperature than normal. So because of that, there is a degree of uncertainty in your measurement. But how do you get the 0.3? Well, it's compared to the mean. So what we need to do to find out why it's 0.3 is look at the actual trials that we get. So if you look at trial number 1, 16.2, that is 0.3 degrees underneath the mean. So when we get a value of 16.2, it's because 16.5 minus 0.3 equals 16.2. If you look at trial 3, it's 16.8. So that's the exact opposite. 16.5 plus 0.3 gives us 16.8. So that's how they've generated this uncertainty of plus or minus 0.3, because it's the largest value from our mean, 16.8, and the smallest value from our mean, 16.2. So this takes into account, of course, our trial 2 and our trial 4, because it's within the range. So if we were to actually draw it using our numbers, you'd have our mean 16.5, our highest value 16.8, our lowest value 16.2, and then of course 16.4 and 16.6 all are within that. (2.6) What type of error is shown by the results in table 3? Tick one box. Well, we have to look at our different types of errors now. The first one says random error. So what could be the reason why we have these different results? Well, it's not going to be any issue with the equipment, because in our method they haven't said anything about that. It's not going to be a zero error, which was what box 3 was an option for, because in our equipment it didn't say anything about using the balance, which could potentially give us a zero error. But from the results now, the values are very close to each other, so the most likely answer is that it's going to be a random error. Question 3. This question is about making a soluble salt. 3.1. Plan a method to make pure, dry crystals of zinc chloride from zinc carbonate and a dilute acid. 6 marks. So what we are going to be writing is a plan for a required practical, and the required practical is crystallization. So what does crystallization involve? Well, crystallization involves first reacting, then filtering, then heating, and then cooling. So we have to describe all of these steps in order, in detail, to aim to get 6 marks. So let's read it again, and then let's think about what we could actually be using in terms of reagents now. So what are we going to actually be reacting? Because that's what we're starting off with. Well, we want to make zinc chloride. We're going to start with zinc carbonate and a dilute acid. Well, the name of our salt is given, zinc chloride. The name of the metal that's in that salt, zinc, is also there. So we need to think about what acid would make zinc chloride. Well, it's got to actually then be hydrochloric acid. Because that's where the chloride in our salt comes from. So the first thing that we want to do then is you want to react zinc carbonate with hydrochloric acid. Now, we want to be a bit more careful in our description here of what's going to happen. So what we're going to actually have is a beaker with a certain volume of hydrochloric acid, and then we're going to add the zinc carbonate into the beaker. But we want to keep on adding the zinc carbonate until it's in excess. Now, what does excess mean? It means that there's so much of the zinc carbonate that there's no more zinc carbonate dissolving in the acid. So let's describe this now. Add the hydrochloric acid to a beaker and add zinc carbonate to the acid. Now remember that even though we're adding the zinc carbonate to the acid, we want to make sure that it starts to dissolve. So we're going to stir whenever we add the zinc carbonate. Then keep adding zinc carbonate until it is in excess. And then in brackets, we just want to make sure that we know that it's in excess. As in our beaker, we should expect to see a solid appear at the bottom of our beaker. Okay, so we've done our reacting description. It's now time for filtering. So how can we filter this here? Well, we would use a conical flask and we would use a filter funnel with some paper. So when we pour our mixture, the solid, which hasn't dissolved, should start to remain in the filter paper, form our residue, and then whatever has dissolved, that will form inside the conical flask. So filter the mixture. So undissolved zinc carbonate separated, dissolved zinc carbonate. Okay, so we've done the filtering. The next thing is the heating. So for us to heat now this mixture, there's going to be a solution at this point. We want to transfer that to an evaporating basin, evaporating dish, and then that is going to go on top of a tripod. Then we'll have Bunsen burner. So transfer mixture to evaporating basin and heat mixture using Bunsen burner. Now, what are we going to wait for when we heat this mixture? We're going to wait for evaporation to have occurred. And how we know that that is occurring, or we should expect our liquid to decrease in its volume, and then we should start to see solid appear. And those will be these solid crystals. We're going to wait until crystals begin to form and liquid evaporates. And then, with the heating described, the only thing left to do is to let it cool and the crystals to form. And there's our method describing how we perform this crystallization process. This is a very common question that you'd expect to find in exam questions, in papers. So make sure that you're familiar with crystallization. The only differences that you might find is that the questions would have different salts that you want to make, different reactants that you would have. 3.2. Name two other substances that can each be reacted with a dilute acid to make zinc chloride. Do not refer to zinc carbonate in your answer. We can't refer to zinc carbonate because we've just been doing that. So what else could we use with a dilute acid, which we know is actually going to be hydrochloric acid, to make zinc chloride? Well, our answers have to all have zinc in there. So what else can react with a acid to make a salt? Well, a perfect example would be zinc oxide, because that would be a metal oxide. But then other than that, it would actually just be zinc on its own. Because a metal and an acid will give you a salt and hydrogen. And then a metal oxide and an acid would give you a salt and water. Question 4. This question is about hydrogen and compounds of hydrogen. Figure 3 shows the displayed formulae for the reaction between hydrogen and chlorine. Table 4 shows the bond energies. So we're given the bond energies for each of the reactants and the products. 4.1. Which expression shows how to calculate the overall energy change for the reaction in figure 3? Use table 4. Tick one box. So typically we'd actually be asked to calculate the total energy change, but in this question here, they just want to find out what expression it would actually be. So what we can do is we can use table 4 as they've asked us to figure it out. So the first thing that we need to remember now is, how are you going to find overall energy change? Well, to find overall energy change is going to be reactants minus products. So realistically, we are trying to look for one of the expressions that has some values subtracted from other values. So if you look at the first one, there's no subtraction there, so it can't be that. Look at the second one, there's no subtraction, so it can't be that either. So we already know that it's got to be one of these two bottom ones here. So let's go back to the table now and use figure 3 and identify them. So our HH bond, the bond energy for that is 436. Our chlorine-chlorine bond, the energy is 346. And our HCl bond is 432. But as you can see, there is a 2 in front of our HCl. So that means that it actually be 2 multiplied by 432. So remember that our reactants, which in this case is hydrogen and chlorine, we need to find the total for that. And then we would need to subtract that from our products. So here is our expression. Which one matches that? As you can see, it is the fourth one. (4.2). The reaction between hydrogen and chlorine is exothermic. Explain why this reaction releases energy to the surroundings. So they just reminded us what exothermic actually means. It's releasing energy to the surroundings. But why is the reaction above, this one here, why is this reaction in figure 3 described as exothermic? Why is it going to release the energy to the surroundings? Well, let's remind ourselves of what actually happens in a reaction. In any reaction, you're going to have reactants and bonds are going to break in the reactants. So this HH bond is going to break, this Cl-Cl bond is going to break. What's then going to happen is you're going to form products. And in the products, you're going to get bonds made. So this HCl bond, and 2 of them to be precise, are going to be formed to get the reaction to be completed. But if it's an exothermic reaction, using our bond energy calculations, we would expect then our overall energy change to actually be a negative value. So if it's a negative value, this means then that the energy from the products would actually be greater than the energy from the reactants. Now remember what we just said here. Bonds are broken from reactants. Bonds are formed for products. So that means then that the energy that's going to be transferred when we're forming these bonds is going to be greater than the energy that's transferred when the bonds are broken. And that is what the reason is for an exothermic reaction. So let's put this into words and get our 2 marks. So the principle, which we described already, is energy is needed to break bonds and energy is released to form bonds. And as we said, the energy transferred when forming the bonds is greater. (4.3) Figure 4 shows part of a reaction profile for the reaction between hydrogen and chlorine. Complete the reaction in Figure 4. You should label the activation energy, label the overall energy change. Right, so we need to complete this reaction profile. Well, first thing that we need to do then, when we're thinking about reaction profiles, is identify, is it an exothermic or endothermic reaction? Well, as we just answered the first question with, it's an exothermic reaction. So we need to remind ourselves now, how would the products be in terms of its position in this reaction profile? As we know that our reactants are here, hydrogen and chlorine. So whenever we have an exothermic reaction, exothermic is RAP. Reactants above products. So that will mean now that our products should be below our reactants. So we need to have a line which is below our products, and that would be below our reactants, and that would represent our products. And what we can do is we can label this line with products, or specifically HCl. The next thing that we want to do then is finish our line to connect the energy. However, we need to do the following things that they've asked us to do. We need to label the activation energy, and we need to label the overall energy change. Well, what's the activation energy? What is this? It's the minimum energy required to start the reaction. How can we identify this from our energy profile? Well, it's going to be the difference in energy from our reactants to the peak of our curve. So what we want to do is just do a vertical line connecting those 2 areas and label this with activation energy. And then lastly, what's our energy change going to be? The overall energy change. Well, it's got to be the difference between the reactants and the products. So then we've got to do another vertical line, and this vertical line has got to be connecting our reactants and our products. And this will be the overall energy change. If it was an endothermic reaction, then it would be the opposite of RAP, which is PAR, products above reactants. So there's a nice little way for you to remember how you should be doing energy profiles for those 2 types of reactions. 4.4. Draw a dot and cross diagram for a molecule of hydrogen chloride. Show the outer shell electrons only. So it's hydrogen and chlorine that are going to be used to make hydrogen chloride. Well, if we're doing a dot and cross diagram, it's either going to be for ionic compounds or covalent compounds. So we have to identify what hydrogen chloride is going to be. Well, if it's ionic compounds, it's going to be non-metal and a metal for ionic compounds. And for covalent bonds, it's going to be non-metals only. So non-metal only. So hydrogen, non-metal. Chlorine, non-metal. So we know we need to do covalent bonding here. So that means that we're going to be overlapping our atoms. So let's take our two circles, one for hydrogen and one for chlorine. But we have to show the outer shell electrons only. So hydrogen only has one electron that it can share. So we use our dot to represent the hydrogen electron. Hydrogen wants to have a full outer shell, so for a full outer shell it would need just one more electron, which chlorine will be able to give. But chlorine has an outer shell with 7 electrons in there. It's already sharing 1, so we need to show 6 more. So 6 more crosses, and there's our dot and cross diagram for hydrogen chloride. (4.5) Figure 5 represents molecules of methane and of polyethylene. Methane is a gas at room temperature, but polyethylene is a solid at room temperature. Explain why methane and polyethylene exist in different states at room temperature. Right, so once again, methane is a gas, polyethylene is a solid at room temperature. So the same temperature, they have different states. Well, why? Well, polyethylene is a polymer. And remember what a polymer is. Polymer is repeating units of a monomer. So this N could be any number of these repeating units. So it could be as small as 5, but could be as large as 100 or more. So that means now that it's going to have a lot more bonds, and it's going to be larger than methane. So let's start with describing that. Polyethylene is a larger molecule. Now, if you said that polyethylene is a larger molecule, that obviously means then that methane is a smaller molecule. Now, how's that going to be linked then to their states? Well, as I was just saying, if it's larger, it's going to have many more bonds. But we're not focusing on the covalent bonds, because these are both covalent molecules here. We're focusing on those smaller intermolecular forces that we would find between the molecules. So the next thing that we want to talk about are those intermolecular forces. So if it's got more in polyethylene, overall they're going to be stronger. The next thing then is polyethylene has stronger intermolecular forces. Now let's think. Polyethylene is a solid at room temperature. It has stronger intermolecular forces. So if room temperature we take to be about 20 degrees, at 20 degrees, there's going to be no melting of this polyethylene. At 20 degrees for methane, it's going to be turning to a gas. So it's gone past the solid phase. So what does that mean in terms of forces now? It means that the forces, when polyethylene is present, are not going to be broken. Whereas for methane, they would be. So for it to actually turn from a solid to a liquid, for example, it would need a greater temperature than 20 degrees. So it would need, because temperature is a measure of thermal energy, it would need more energy to break those intermolecular forces. So what does this ultimately mean then? The 2 points, the point to turn a liquid to a gas, which is the boiling point, which is the state before a gas, and the melting point, which is the temperature needed to turn it from a solid to a liquid, these are going to be different for the two molecules that we have here. And that difference is going to be that for polyethylene, they're going to be higher. Question 5. This question is about acids and alkalis. 5.1. Ethanoic acid is a weak acid. What is meant by a weak acid? Answer in terms of ionization. So it's a definition of a weak acid. You should know definition of a strong acid and weak acid, but we need to just give weak acid now. So our weak acid is going to partially ionize in a solution. And specifically, what we mean is an aqueous solution, so something that's dissolved in water. How is this going to be different from a strong acid? The strong acid would strongly or fully ionize in solution. .2. The concentration of an acid can be measured in moles per decimeter cubed. Which combination of changes increases the concentration of an acid? Tick one box. Well, it's great that they've given us the unit for concentration here because we can use this to help us. So let's write the concentration unit like this, moles per decimeter cubed. And then what we can do is you can go through each of these options and then figure out if that will work with our unit here. So first one, the mass of acid dissolved is halved and the volume of solution is halved. So we're decreasing, because we're halving, the mass of the acid, so that means that the moles will go down. And the volume is halved, so the volume will go down. Will that cause an increase in the concentration of the acid? Well, no, it's not going to, because both of the factors are decreasing. Number 2. The mass of the acid is dissolved is halved, so decreased, and the volume is doubled. Will that cause an increase in the concentration? Well, both things are doing the opposite, so it's not going to increase the concentration, it's just going to stay where it is. So that's not correct. Number 3, the mass of acid dissolved is doubled, so increased, and the volume of solution is halved. So that means it's decreased. So if we've decreased the volume now, and we've increased our molarity, that is going to cause there to be an increase in the concentration. So that is going to be an acceptable answer. But let's just check our final one to see if that is true. The mass of acid dissolved is doubled, and the volume of the solution is doubled. So the volume is doubled this time. Concentration is going to not increase because we're increasing the volume that this acid is going to be dissolved in, so it's not going to increase the concentration. So our third option is definitely correct. 5.3. The concentration of an acid can be determined by titration. An indicator is added to an alkali in a flask. Name an indicator that can be used in this titration. Give the color change of the indicator when acid from a burette is added to the alkali in the flask. Well, titration is all about neutralization. Mixing an acid and an alkali and then finding the exact point at which it is actually neutralized. So we need to just give an example of an indicator that can identify that point and then what the expected color change would be. Well, a perfect example of an indicator would be methyl orange. So what's the color change going to be from? Well, methyl orange actually starts as a yellow solution. But when the acid is added, the endpoint for neutralization will be for it to turn red. Another example of an indicator that you could use is phenolphthalein solution. When there is no acid, the solution is appearing pink. When the acid is added and is fully neutralized, it will then turn colorless. (5.4) Sodium carbonate dissolves in water to produce an alkaline solution. Give the formula of the ion that makes the solution alkaline. So remember water. Whenever we have water, it's a neutral pH. pH is 7. Water is made from two ions, our H plus ion and our OH minus ion, which is a hydroxide ion. All acids will contain hydrogen. So this is the ion that we find in acids. So hydroxide is the ion that we find in alkalis. So the ion would be the hydroxide ion. 5.5. A student does a titration using sodium carbonate solution and nitric acid. The equation for the reaction is shown. 25 centimeter cubed of a 0.124 moles per decimeter cubed sodium carbonate solution is neutralized by 23.6 centimeter cubed of nitric acid. Calculate the concentration of the nitric acid. Give your answer to 3 significant figures. You should calculate the number of moles of sodium carbonate in 25 centimeter cubed of solution, the number of moles of nitric acid in 23.6 centimeter cubed of nitric acid, the concentration of the nitric acid in moles per decimeter cubed. 5 marks. So, what we're going to do first is we're going to take our equation and we're going to identify what we have been given in the question for each of the substances in our equation. Now realistically, because we're dealing with a neutralization here, we only really need to focus on the reactants, because we want to find out how much acid will neutralize how much alkali. So for our sodium carbonate, what piece of information have they given us? Well, they've given us the volume, 25 centimeter cubed, and they've given us the concentration, 0.124 moles per decimeter cubed. So let's just write that underneath our first reactant. And we can do the same thing for our next reactant. So for our nitric acid, what are we given? We're given the volume only, 23.6 centimeter cubed. We're not given a concentration. That's the thing that we're trying to find right now. Now, for us to find out how much nitric acid in terms of concentration we need, as they told us, we need to find the number of moles. So we're going to start by trying to find the number of moles. So for us to find the number of moles now, we need to use the equation. Number of moles is equal to concentration multiplied by volume. However, the problem that we have right now is that we can't take the two numbers as they are and put them into the equation because there's a difference in the unit, specifically the unit of volume. So what we're going to do first is we're going to convert our volumes into decimeter cubed for them to then be used in the equation. So 25 centimeter cubed, we want to find that in decimeter cubed now. So to convert centimeter cubed to decimeter cubed, we need to divide by 1,000 always. So 75 centimeter cubed would actually be 0.025 decimeter cubed. So there's our volume. We're going to multiply that by the concentration of sodium carbonate, which is 0.124 moles per decimeter cubed. Plugging that into our calculator now, that will allow us to calculate a moles. Our number of moles then of sodium carbonate will be 0.0031 moles. Now, for us to find the number of moles of nitric acid, which is the next thing that we're going to do, we need to find the ratio of number of moles of sodium carbonate to nitric acid. For us to do that, we are going to be looking for the numbers in front of our reactants. So in front of sodium carbonate, there is no number. So that means that we have 1 mole. And that 1 mole is 0.0031. But in front of our nitric acid, we actually have a 2. So that means for every 1 mole of sodium carbonate, we have 2 moles of nitric acid. So that's the molar ratio, 1 to 2. So if we have 0.0031 moles of sodium carbonate, we should have double that for nitric acid. So 0.0031 multiplied by 2 will be 0.0062 moles of nitric acid. So we've now calculated the number of moles of nitric acid. What's the last thing that we want to do now? We need to then calculate the concentration of the nitric acid. And to do that, we can use our equation again. Number of moles is concentration multiplied by volume. So what have we got this time? Well, we've got the number of moles. Our number of moles of nitric acid is 0.0062. Our concentration, we don't know, we're trying to find that. Our volume is 23.6 centimeter cubed. However, just like before, we need to convert to decimeter cubed because the answer that we need is in moles per decimeter cubed. So 23.6 divided by 1,000 is going to be 0.0236 decimeter cubed. So that will be our volume value. So we're then rearranging to find the concentration now. So it's going to be 0.0062 divided by 0.0236. Doing that now, we will get a value for a concentration of 0.2627. Continuing. But our concentration, they said to us we need in 3 significant figures. So 3 significant figures from this would be 0.263. When hydrochloric acid dissolves in water, hydrogen ions and chloride ions are produced. 5.6. A solution of hydrochloric acid with pH 4.5 has a concentration of hydrogen ions of 3.16 times 10 to the power minus 5 moles per decimeter cubed. What is the concentration of hydrogen ions in a solution of hydrochloric acid with a pH of 2.5? So they've said in the question, a pH of 4.5 gives us a concentration of 3.16 times 10 to the power minus 5. We need to find out what is a concentration when the pH is 2.5. Well, normally what we would do is we'd find out the factor between these two values and then use that same factor to find out our missing value. Well, we can do this slightly. We can easily see that to go from 4.5 to 2.5 is we're dividing by 2. And this 2 is useful for us. But it doesn't mean now that we can take that same factor and divide this value by 2 because we will not get the right answer. The reason why we'll not get the right answer is because of how pH works. pH works through powers of 10. So that means now that if we have a pH that has decreased by 1, that means that our concentration has actually changed by a factor of 10. And it's actually increased by a factor of 10. Because as the pH decreases, the concentration of hydrogen ions increases. So look at our difference, it's a factor of 2. So that means then it's actually, because we've decreased by 2 this time, it's actually going to increase by a factor of 100. So what we would need to do then is change this value, 3.16 times 10 to the power minus 5. Need to increase that by a factor of 100 now. So that would be 3.16 times 10 to the power minus 3. And that would be a concentration of hydrogen ions value. Interestingly, to check that this pH actually has this concentration, there is a formula that you could use, which you don't need to know. To calculate pH is equal to minus log of the hydrogen ion concentration. So if you were to put into a calculator minus log of 3.16 times 10 to the power minus 5, it will generate a pH value of 4.5. To check then your answer is actually correct, what you could then do is do minus log of 3.16 times 10 to the power minus 3, and it should give you a value of 2.5, and that would confirm that you're correct. 5.7. Which element has atoms that have the same electronic structure as the chloride ion? Use the periodic table. So chloride ion, as I said in above, is Cl-. So find chlorine first in the periodic table. We know that it has 17 electrons in total. But if it's a chloride ion, it has an extra electron. So that means that there are 18 electrons for chlorine. Which atom from the periodic table then would also have 18 electrons? So looking at the periodic table along, the next atom that's close to chlorine with the atomic number of 18 is argon.